Hi, my name is James Davis, and I will be presenting the usage cases for a star-like envelope of a family of curves. Now, I researched this with my mentor, Pedro David Bello Maldonado, and I am, of course, recording from Marietta, Georgia. So let's get right into it. I started thinking about this 7 years ago, back in elementary school in the fifth grade in the math club. So I was in the math club, and my teacher, who happened to be the head of the math club, she suggested after the meeting, because she pulled me aside because she knew I loved math. I've always been a little bit of a math nerd, and I'm very proud of it. But she suggested that you could make a curve out of straight lines. Now, obviously, as a fifth grader who didn't know what calculus was yet, I did not know this. And I was like, that's preposterous. But she showed me an interesting shape, which I'm going to explain to you. And it's essentially a bunch of straight lines interconnected that look like a curve but aren't. So 7 years later, I'm in high school and I'm revisiting this, and here's how it's made. Given a value n, you draw lines from 0 to n, from 0n to 1, 0, 0n minus 1 to 2, 0, 0n minus 2 to 3, 0, and so on until the final line from 0, 1 to n, 0. And if you see the star-like shape in the center of that graph, you will notice that if you do this process, it'll create the star shape in the first quadrant. Now you can reflect that shape in the first quadrant to make the whole star, and then to make the circle, what you do is reflect the shape on in the first quadrant across the line y equals minus x plus n, or for other quadrants across a diagonal line connecting the points with the highest x value and the highest y value, their absolute values. And here's an animation of how it looks. As you can see, it starts to look like a curved shape the more lines intersect. So I wanted to construct this formulaically. What I wanted to know was, is there a way that I can make this in one formula so I can manipulate this to study it? And what I ended up doing was defining it parametrically. First, I took the derivative of the star shape. So that'll give you obviously the star shape is not differentiable on all points because there are points where they intersect with each other, but we can represent it fairly well as y equals floor of t minus n over floor of t plus 1. And you can represent the x-axis as the x values as t squared plus t over n plus 1. Now what these each individually mean, y of t is the slope of the line segment, so you have minus 10, then minus 9 halves, then minus 8 thirds, and so on and so forth. And then t squared plus t over n plus 1 is the intersection points. So you have your intersection with the y-axis and the first line segment at 0 minus 10. Well, no, sorry, it's 0 at x equals 0. And then you have your next one at, let's say if n equals 10, then you'd have it over 2 11ths, at x equals 2 11ths. Now, I rearranged this to be a function of y with respect to x, in terms of x. So you have, what I did was define t in terms of x first as square root of n plus 1 x plus 1/4 minus 1/2. And then I substituted that into the equation of y of t. So once I did that, I represented y as g of x, and I took the integral of g of k with respect to k along 0 to x. And then I added n to it. And that's how you end up getting the first quadrant star-like shape. After that, you do the reflections I mentioned previously, and you get this. Now, this shape has interesting properties. Both the star and the circle retain their properties. But the point on the star furthest from the origin is always going to be on y equals x. So if you draw an imaginary line with the slope of 1 through the origin, you'll notice that the furthest point from the origin is on that line, y equals x, although it doesn't necessarily look like it. We have done several simulations for any value of n, and we did a little bit of a proof that shows that this shape retains its properties for all values of n. So next up, in order to study this further, because as you increase n, the size of the shape is also going to increase. But what if we only wanted to increase the line segments? So we defined a value m that only represents the number of line segments, whereas n represents the size of the shape. And what we found when we increased m was that for any value of n or m, there is a rotated parabola that intersects the midpoint of each line segment every time. So this is where an envelope of a family of curves comes into this. An envelope of a family of curves is a function that is tangent at some point or another to every to every curve in the family of curves. So if you look at these two graphs, they're a little bit hard to distinguish, but the red line is the envelope and the black line is the star-like shape. As you can see, the red line is tangent with the midpoint of every line segment in the star-like shape. And if you look at the second graph, this is at n equals 10. As you'll notice, it's a lot closer. And as n approaches infinity, it converges towards the envelope. Now, obviously, we can't model this as n equals infinity, so instead we modeled it as m equals infinity. And just as we guessed, it converged to the envelope. A parabola rotated 45 degrees. Now, because of the limitations on this, given that it's a parabola rotated 45 degrees specifically, it's limited in scope, but it's useful. It reduces computational time, it reduces energy and memory needed. It's especially useful in data-heavy calculations, because imagine trying to use rotational matrices to approximate values on a rotated parabola. If you used rotational matrices, that would be a lot of calculations. That's why matrices are so, power intensive. Especially for artificial intelligence, if you've taken a look at that. Matrices, they essentially run on matrices, and that's why the artificial intelligence is so power intensive. But imagine trying to model 1 point. Compare that to 2,000 points. Compare that to 4 million. If you're just doing 1 point, it's not that bad, but 4 million points on a rotated parabola would be pretty intensive to calculate. So this reduces time complexity. Now, we can also do this in pixel rendering in rendering pixel graphics. If you take a look at the graph right there, this is the star-like shape juxtaposed with a circle, and they're practically indistinguishable, that outer segment of the star-like shape. All it takes is a very slight modification of the shape, which you can check at the link that I have in the center of the graph. That link leads to other research that's been done on rendering pixel graphics with this star-like shape in a circle. And the integer-only arithmetic eliminates the need for embarrassingly intensive parallel floating point calculations for this circle. What this will do is it reduces algorithmic complexity from O of k squared to O of k log k, which is essentially, k squared, for those who don't know what time complexity is, k squared is essentially saying that it'll be proportional to the square of the number of comparisons that you would make. The number of comparisons is proportional to k squared, where k models the number of items that are needed to compare. So we reduce that from k squared to O k log k, which for very large calculations, for large sets of values, this is super helpful and has a surprisingly small error bound, where the error bound is the upper limit on the errors of the between the approximation and the actual value. So this star-like shape actually has a lot of convenience. Although it's limited in scope, it can be used to reduce complexity, memory usage, power usage in large-scale calculations for stuff like this. Thank you all for listening. I had a wonderful time presenting this, and I hope you all have a great day.